Hey MTech, this is Skylar Tibbits. I'm here at the Self-Assembly Lab, and I'm going to show you around the lab, introduce you to some of the work, and then do a bit of a voiceover of some of the projects. So the Self-Assembly Lab focuses on a few different principles. One of those is self-assembly, which you can see in the tank over here. By the way, this is Dimitris here, and Christoph. And so I'll try to show some of the different principles. So this is a study looking at the self-organization or self-assembly of these components. It's in a 500-gallon tank of water with different pumps that we can activate to assemble themselves. And we have all different studies that we do on the intensity of the pumps or locations, the shape of the modules, etc. Another principle that we look at is what we call programmable materials, how to program the shape and property of materials so that they can transform. We've done some research recently with Christoph on some self-morphing shoes for textiles and programmable carbon fiber and wood. Behind me you can see some images of some of the 4D printing work. That's Jared, by the way. The 4D printing work, the idea was that you multi-material print and then you activate it with moisture and they self-transform, they change shape and property. And then the last category of research that we've been investigating is what's called granular jammable materials, how you can jam particles so that they can change from a solid to a liquid and back to a solid. So in the lab here, some of the things that you see, there's large-scale printers. That's a 4-foot by 2-foot multi-material printer. Dimitris is working on a small robot arm, doing different pick and place and camera movements. This is some of the self-assembly research, some of the granular jamming research. We have gases to make things float for the aerial assembly work. We have filament extruders and shakers and tumblers, heat plates, furnaces for programming metals, different printers over there. This is a beta of the Form 2, and we have Form 1 SLA printers, etc. So now I'll try to introduce you to some of the other work and explain some of the projects. So I'll give you a little bit more background about the research, how we got into this and where we're going with it. One of the first things we started to study is how design tools can transform the way we design and make. This is one of the first CAD tools from Sutherland in 1963 at MIT. It's called Sketchpad. And that has more contemporary counterparts like software and computational tools that allow us to simulate fairly complex phenomenon. We can analyze things, we can design structures that we never could have designed before simply because code has radically changed the way we design. But similar to that, this is one of the first CNC machines from MIT in the 60s as well. The first time they connected a computer to a machine, and that radically changed the way we make things. It has contemporary counterparts like multi-material printing, CNC routing, laser cutters, water jets, etc. So code has also radically changed how we make things. So we think about that as code for design, code for machines, and where we're trying to go is code for construction. This is a quick film of us assembling a prototype for the 150th anniversary of MIT, which I think is the antithesis to our work in many ways. It's brute force, blood, sweat, and tears, lots of rivets, lots of bolts, slamming stuff together. And this is kind of the opposite of how we want to construct in the future. So we're looking for the future being code for construction, smarter materials that can be programmed to change shape and property, or materials that can assemble themselves. So we focus on a few different phenomena. One is self-assembly, as the lab's name suggests, which is a process by which disordered parts build an ordered structure through only local interaction. Probably the most clear example of this is a project we did with molecular biologist Arthur Olson. So this project, there's a flask, you shake it hard and the parts break, and then you shake it a little bit softer and they come back together. To us, this demonstrates that you can build non-random structures through random energy. So you don't have to know anything about the structure, you don't have to be an expert, you don't have to be precise, you don't need expensive robotic precision assembly tools. You can shake things wildly, randomly, and build precise, repeatable structures. So in this project, we were proposing that we could have large structures that would float around in the airspace above our site, and they would assemble themselves. And then as the helium died, they would come back to the ground and build space frames much larger than them and much more stable. So we can assemble large-scale structures in air. The second category of research that we look at is what's called programmable materials, how to program materials to change shape or change property by design. Probably the fundamentals of these that everyone can understand is really a simple set of ingredients. So on the left-hand side, we utilize materials and geometry, just like everything in our physical environment. You may start with, in an application, some material like wood, and then you think about how you can activate that through energy, so moisture, for example. Or you can start at the energy, you might say we have heat, and then what materials will react to heat? You can think about metals or thermoplastics, etc. And then we design the geometry, the micro and macro architectures of those materials in combination with one another to develop functional mechanisms, so folding, curling, stretching, or shrinking. And we combine this all to be able to program geometrically and materially materials to transform in form and function. Our most notable work to date is what we call 4D printing. So 4D printing was a collaboration with Autodesk and Stratasys, where we were trying to multi-material print structures so that they could change shape and property over time. So 4 meaning time. This is much like printing robots, but no wires, no motors or electronics. It's also sort of like printing smart materials, but we want to be able to fully customize those smart materials so they can be activated by different energy sources or transform in different ways. So we printed everything from single strands that fold into 3D cubes to single strands that fold into text like MIT, surfaces that fold into truncated octahedron, surfaces into saddle shapes, surfaces into doubly curved structures like the contours of the body or automotive or aerospace panels, 50-foot long strands in Olympic swimming pools, nearly any shape you can think of from 1D to 2D, 1D to 3D, 2D to 2D, 2D to 3D, 3D to 3D, all sorts of different shapes from one thing to another using folding, curling, stretching, shrinking. These are all activated by water. But a main question kept coming up. How do we program every material or any material? Many companies started coming to us from different industries asking how we could program different materials, how we could use different industrial processes. So we started a much larger collaboration, which we call Programmable Materials, with the vision that we want to be able to make any material a smart material. We want to program materials to change function and property, and we want to make them easy to produce, readily accessible, cheap, etc. This is now an ongoing collaboration with a number of different people, from product designers to mathematicians, computer scientists to materials developers to software companies, etc. So we're developing this collaboration with a number of different materials. So far we've shown programmable carbon fiber or composites like Kevlar, fiberglass, etc. Shape-changing textiles, and wood. With wood, we actually print the wood. So we essentially print out an MDF-like filament. It's a mixture of sawdust and plastic. We extrude that so that we can print the grain of the wood. So we can get diverging and converging and 2D and 3D structures of the wood. And then we print it in different shapes, and when we activate it with moisture, it then curls, folds, twists into very precise shapes. So you can make wood fold to any arbitrary shape, or you can make self-folding furniture or self-folding product design details. With textiles, there's a few different ways to do it. The most simple is that we use a pre-stretched textile. We print on top of that textile, and then that material property and the pattern of the material allows it to transform in 3D shape. So when you simply cut it out, it then jumps into shape. So this is an example we did with product designer Christoph Guberin, where we were printing on the textiles to make shoes. So we showed these shoes that could be made from flat sheets of textiles that self-form, so there's no molding, there's no forming or stitching, and they can morph around your foot. Another way to activate textiles is similar to what we do with carbon fiber. So we have this large 4-foot by 2-foot multi-material printer. We can roll out sheets of material and print active polymers. So this is a collaboration with a company called Carbitex who makes flexible carbon fiber, and we can make it now light active, heat active, or moisture active. So the flexible carbon fiber opens and closes in this case for an active shading application when it gets exposed to light, like sunlight from the environment, for example. A last topic of research that we've been investigating is what's called granular jammable materials. So that's pretty well known to most people. If you go to the grocery store and you buy coffee, it often comes in a vacuum pack. So the vacuum is pulling pressure on it and it feels like a brick. It feels really rigid. So all the particles are jammed next to each other and they act like a solid. When you open it, you can pour it like a liquid, so all the particles flow out. That's a principle that allows materials to go from solid to liquid and liquid back to solid. So we tried to start utilizing that at much larger scales. We started a collaboration with Gramazio Kohler Research at ETH Zurich on a project called rock printing. And the idea was we wanted to use granular jammables at much larger scales, but we wanted to remove the vacuum and remove the membrane that's typically associated with granular jammable materials. So what we do is we print with rocks. Essentially, it's like a big powder printer. We spread rocks layer by layer, and then we spit out string. So it's loose string without any binder or adhesive, and we spit that out robotically on each layer of the rocks. So here you'll see a video of a recent project that we did at the Chicago Architecture Biennale with Gramazio Kohler. So there's a 4-meter tall chamber, and we're spreading rocks and spitting out string layer by layer to fill up this chamber. And then we remove the chamber, and all of the rocks that did not have the string fall away, and then all of the rocks that did have the string stay, and they jam in place to make a load-bearing structure. So you can put 3 tons on top of this 4-meter tall column, and it acts like a solid. So it's fully in compression, the string is taking the tension, and it acts like a rigid solid. Then when it falls over and it hits the ground, it disintegrates like a liquid. And what we were interested in is reversible concrete. So you can pour this like a liquid, it instantly cures, so there's no curing time, and then you can reverse it. You can vacuum it up and move it wherever you want and pour it again. So where do we think all of this craziness is going? To me, this image is really the epitome of where we are today in construction and manufacturing, or even where we are with material components. We have lots and lots of materials, lots and lots of components. They each do different things. We've designed them to be static, and if they're active, they're electromechanically active, taking lots of power and motors and sensors or electronics or components. In terms of assembly and construction, we have super complex details and complex assemblies that need more and more skilled labor or more and more high precision robots. And this is really the antithesis of our work. We want to have less components. We want to have less energy or passive energy sources like heat, moisture, temperature, light to activate these systems. We want our materials to be smarter. We want them to be highly active and adaptive. We want them to help us assemble better things, more agile and resilient or adaptive structures. We want them to allow us to assemble things in better ways, and that potentially could propose that the materials could assemble themselves from scratch. One of the major shifts that we're seeing right now is a shift away from a robotic-centered mentality towards a smarter materials mentality. We've shown that materials can have sensors, actuators, and logic, and therefore behave like robots, but they don't need any of the components or the power or the electronics that robots require. They need less assembly, they cost less, they fail less, etc. So materials are becoming robots. But it also means that there could be a collaboration between robotics, materials, and humans. So robots are great at precision, repeatability, they don't get tired, they're great at global communication, etc. Materials are really good at physics. Materials occupy the physical world. They can sense things that we can't sense or that machines can't sense. They can respond, they can be sensors and contain information, and they can give information to the robots. And likewise, humans are really good at creativity and abstract thinking and collaboration between all of those three. So we really think about it as a new type of collaboration with materials, not as materials as our slaves. And the last is that we're seeing new phenomenon in assembly. Right now in material science and synthetic biology and DNA origami, self-assembly is huge. It's providing a new opportunity to manufacture and assemble things that we've never seen before. And what we're interested in is proposing self-assembly as a scenario for manufacturing or construction at much larger scales, and trying to translate that into principles for new ways to think about how we put things together across many different domains and across many different scales. So we believe today we program computers and machines, and tomorrow we will program matter itself. So thanks so much. I hope you enjoy MTech. So sorry I couldn't be there. Thanks again.